It's good to be back here at Rutgers. I did my undergrad here. I proved my first theorem across the street, so it's fun to be back. And so I'll be talking about large gaps in formula complexity between depths. And so the motivating question behind this work and this talk is, I think, a pretty basic question. What is the cost of parallelization? You know, you have some computation that you want to run in parallel. How much does it cost to make that more parallel? And I should say, you know, this is an old question. It's a classic question, and there's many lines of work on this. I'm going to be talking to you a little bit about one line of work. Okay. So let me tell you a little bit about how I want to formalize this question. And the model we're going to consider, probably you're all familiar with, but I'll just recap it, is constant depth formulas. So in a constant depth formula, you have some constant depth tree. Each node in the tree is going to be an AND gate or an OR gate, and it's going to have unbounded fan in. And we're going to let the size of the formula be the number of leaves in the tree. So hopefully everyone's familiar with this model. And the quantity I'm going to be interested in is going to be L sub d of f, which is going to be the minimum number of leaves in any depth d formula computing f. So that's just some notation. We have this model, constant depth formulas. You might wonder why this specific model. It's what I can prove lower bounds against, and it's a very pretty natural model. And now we can formalize the cost of parallelization by asking the following question. You have a function f. How far apart can L sub d of f and LD plus 1 of f be? What is the difference between the complexity computing this function at depth d versus d plus 1? Okay. Does everything make sense? Hopefully. Cool. All right. So we have this question. How far apart can LD of f and LD plus 1 of f be? What do we know about this question? So there's the best known result is kind of a classical result coming all the way back in the late 80s by Hofstad. And he showed a very nice result. He showed that there exists a function, in fact, an explicit function, such that its d plus 1 complexity is polynomial. In fact, it's a linear. It's witnessed by a read once formula. But its d complexity is pretty high. So it is 2 to the n to the omega 1 over d. And this is like a classic result, and this is like a nice lower bound. And OK, that's cool. Can we do better? And you might wonder, 2 to the n to the 1 over d is nice, but could we get something better than that? Could we get 2 to the n? Could we get something even more than that? And looking at this question, you might think maybe the answer is no. So the question of improving this 2 to the n omega 1 over d has been like a long-standing open question to get an explicit function that requires formulas of size bigger than that. Getting a gap like this might not be possible. That's what you might think. That's what I thought. But let me ask, a more specific question. Instead of looking at like polynomial versus exponential, what if we looked at a different way to formalize this question? How big can the additive gap be between these two measures? You have a function f. What is the depth d complexity minus the depth d plus 1 complexity of this function? And can we get a function such that this is larger than 2 to the n omega 1 over d? Okay, so that's what I'm going to talk about in this talk.
But Rahul, for the original question, isn't the answer no? Because you can just do divide and conquer.
How far apart the original question?
LD was LD plus 1, because if you just take, any formula that's constant depth is also a formula, and you can just kind of do divide and conquer on it to get 2 to the n to the order 1 over d size formulas.
Well, 2 to the n to the 1 over d. Oh, well, isn't it 2 to the s to the 1 over d?
S, but S is poly of n.
S is poly of n. So but this question still makes sense, right?
Yeah. But I'm just saying that the answer to the original question is no.
Yeah. Yeah. Okay, cool. Right. So how big can this additive gap be? All right. So let's try. What's the first thing you would do? The first thing that you might do, the parity function is something that we understand in the constant depth realm, and in fact, it's basically a version of it is what's being used in that proof by Hofstede on the previous slide. So okay, what happens when you plug the parity function into here? The nice thing about the parity function is that this becomes much easier with more depth. Each time you add an extra layer of depth, it actually becomes kind of like exponentially easier. So that's great. You get a big savings, but unfortunately, it's like just not that hard of a function. Its complexity is only 2 to the n to the omega 1 over d. So if you're looking for a difference between these two quantities to be larger than 2 to the n omega 1 over d, you're not going to have much luck there. And in fact, this is going to be a problem for any explicit function because every explicit function, and explicit function maybe means like computable in NP or something like that. We only have bounds like this for those functions. So if you look at explicit functions, it doesn't seem like you can get anyway. All right, so explicit functions don't work. What do we do when we can't do an explicit function? Okay, well, maybe a random function works. Because I'm not asking you to come up with an explicit function that witnesses a large gap. I'm just saying, does there exist a function with this large gap? Okay, so what happens with a random function? Now it's really great. We got 2 to the, this random function is going to require large formulas, so this first quantity is going to be large. But it doesn't really seem that easy to use extra depth to compute random functions better. In fact, my intuition is like a random function should just compute it with a lookup table. And a lookup table doesn't really require a lot of depth. It seems like you can do everything in depth 3. So after depth 3, random functions don't seem to get easier.
But you still get advantage for depth 3 versus depth 2?
Yeah, you still get advantage for depth 3 versus depth 2. Yeah, so at depth 2, there are functions which require 2 to the n, and then after that it gets to 2 to the n over log n. So there's a big gap there, and then after that, it seems, I mean, we don't know, but it seems like there's not much of a gap. Okay, so what? We've eliminated explicit functions, and random functions don't work. What can we do? Turns out you can actually do something. You can show that there exists a function f such that the gap between these two quantities is actually 2 to the omega sub d of n. So this omega sub d means that there is some constant depending on d that's out in front there. I think that constant is something like 1 over 2 to the d, maybe 1 over 4 to the d, or something like that. So we can show there actually exists a function that does this. Okay, yeah?
You want this for every d or for some d?
The theorem is for every d. Yes.
And does it become easier if you just need one d?
I don't know of any way to do that. I mean, definitely 2. So 2 versus 3, you can use the parity function, and then you'll get this gap. But after that, I don't know how to do anything more than that. Good question. Right. Oh. Actually, there's something I should say here with respect to your question. This function is going to change for each d. So it's like you tell me d, I come up with a function, and then that's going to have a d versus d plus 1 gap. It would be cool to get a function which for
Every level increases.
Yeah, every level increases. Yeah, that would be cool. I don't know how to do that, but that might be possible actually. Possible to do. Okay, any other questions? Great. Okay, awesome. So now I will talk about chemistry. So I want to tell you a little bit about this theorem. So I want to tell you a little bit about this function f. And so in chemistry, there's sodium chloride. And so if you know anything about sodium, it really sucks. It's pretty toxic. And if you know anything about chlorine, it also sucks. It's not very good. But you put them together, and you get salt. And salt, which I went out yesterday, I bought some. And just to prove to you guys, I'll be very adventurous. Salt, sodium, chloride. I think this one has iodine too, so extra dangerous. We'll see. A few hours. Will I still survive? Okay. And a very similar thing happens with this theorem. So, okay, yeah, salt is important for living things. Hopefully, you are eating salt. So we have sodium, which is the parity function, which is no good for proving the separation. And we have chlorine, which is a random function, also no good for proving the separation. And together, they make salt. it turns out that this function f is some sort of mix between the parity function and the random function. You like somehow mix them together. I'm not going to tell you precisely how you construct f, but I'm going to tell you what the building blocks are. And you smash these together, and then you can come up with this function that gives this separation. Okay. Any questions there? I can't answer any questions on chemistry, but all right, awesome. So let me tell you a little bit about how you mix functions together. I'm not going to tell you exactly how to construct this function f, but I'll tell you this is like the key ingredient. So I call this theorem an NaCl theorem because you take one bad thing, you take another bad thing, and they're both bad for what you want, but you put them together, and now you can eat them. Exactly. Okay. Okay. So how do you mix functions? And we're going to mix functions using a very classical tool, which is a direct sum. So if you have some function f and some function g, the direct sum of these two functions, or at least the direct sum that I care about, there's various notions of direct sum, is just going to be the and of these two functions on different inputs. So you have an input x and input y. They're not related. And I'm interested in f of x anded with g of y. And the nice thing about working with formulas is that direct sums act nicely with formulas, at least depth unrestricted formulas. So there's this theorem, which I couldn't really find a citation for, I guess it's folklore, that if you have a direct sum, which is h, which is the and of these two functions on independent inputs, then its formula complexity acts as you want it to. So L here just denotes the size of the smallest formula for it. So if you and together two independent functions, you get precisely that the formula is, its complexity is the complexity of f plus complexity of g. Note there's no +1 here because I'm talking about leaves instead of gates. So, right. And the proof of this is actually not too hard. The upper bound, oh yeah, I'm going to skip the proof of this, but if you're interested, it's not too hard. Great. So direct sum, I've introduced this tool to mix together functions. Let me just recap what I've said. There's this theorem that says there exists a function that's like much harder at depth d plus 1 than it is at depth d. I said that function is somehow a mix between random functions and parity. And I've told you kind of the tool we use to mix things together is the direct sum operation. And now I've said, okay, direct sum acts nicely with respect to formulas, but it acts nicely with respect to formulas of unbounded depth. And our critical lemma is going to be talking about how direct sum operates when the depth is bounded. Okay, but that's looking ahead. Any questions so far? Cool. Okay, so now let me tell you about this main lemma. So this theorem we're aiming to shoot for is that there exists a function that's much easier at depth d than it is at depth d plus 1. And we have this tool, which is like the direct sum operation, which says, you hand me two functions, I create a new function h, which is the and of those two functions. And I said it acts nicely if you have the depth unrestricted. Turns out if you restrict the depth, something very interesting happens. So there's a bunch of notation here, so let me just kind of walk you through this. I should also say that this theorem statement at the top is just a reminder of what the theorem statement is. Like the f on this slide is different from the f in the theorem statement. And this lemma is going to be about generic functions f and g. So you hand me functions f and g, and if there's some informal property, I'm not going to state the property, if g is somehow hard relative to f, then what you get is the complexity of h at depth d plus 1. I'm gonna come back to this or on top. I mean, you could probably guess what it means, but I'll come back to it. Somehow the d plus 1 complexity of h is greater than or equal to the depth d complexity of f plus the depth d plus 1 complexity of g. Okay, so let me tell you what that or on top means. This just means the minimum number of leaves in an or top depth d plus 1 formula for h. Oh, I should also say, it's not going to be clear how this lemma implies the theorem. It's I mean, you might be able to see how maybe you can get to the theorem from this, but I'm not going to tell you how to go from one to the other. I just want to tell you about this lemma that is the main building block. Okay, so we have this first quantity, which is the depth d plus 1 complexity if you're restricted to have an OR gate on top. And, just some intuition about this. the function h is the direct sum with an and on top. And I'm saying I'm interested in formulas with an OR gate on top. And somehow, some intuition for this lemma is you need to compute an and on top, or you need to compute an and at the end, but you have an OR gate on top. And so somehow this top layer of depth is kind of not very useful. And what that lets you do is, and what we can prove is, you can actually get a lower bound where the dependence on f is actually in terms of the depth d complexity of f. So you're lower bounding the d plus 1 complexity of h in terms of the depth d complexity of f. And that's what's really powerful about this lemma. Somehow it's saying like you can like lift lower bounds from depth d to depth d plus 1 using this. And I should say, this inequality actually ends up being kind of tight if g is a random function, a random function on sufficiently large number of inputs. And so that's where this random function is coming in the picture. So at the bottom level, what we'll do is we'll let f be the parity function, we'll let g be a random function, and we'll smush them together to get h. You'll do a few other tricks on h, and then you'll try and repeat this going up further and further. OK. And then, yeah, so that's how you use the lemma. You're going to somehow use this lemma to lift, and it's not going to be obvious how to do this, lift large depth 2 versus depth 3 separations, which we have for parity, into higher and higher separations. And I should say this is kind of it actually turns out to be very delicate. You don't want to use purely random functions. You want to use kind of these very specific functions that come from Lyapunov's depth 3 formula upper bound. But whatever, don't worry about that. There's just, yeah, it's kind of delicate. OK, any questions about this lemma? Yeah.
So is the hard function, the function that gives the separation, is going to look more like h then?
Yeah, it's going to look more like h. It's going to be some sort of composed h. It's going to be like you're going to direct some things. You're going to do a few more tricks. I haven't told you what those tricks are. Then you're going to direct some what you had before with something new, and then you're going to keep direct summing it. Yeah.
I know you just told us not to worry about this, but
yeah.
Is there a part in the proof
Yeah.
where you were substituting in a random function for g,
Yeah.
and then because of the Lyapunov bound you couldn't proceed, and that like forced you to pick Lyapunov functions instead of truly random functions? Is it that clean, or was it?
Yeah. So what happens is the tightness of this inequality is basically you might how far away the d plus 1 complexity of g is from the depth d complexity of g.
Mm-hmm.
So it turns out what you want is some function that kind of looks like a random function, but has roughly optimal depth 2 formulas. So the way we do it is like yeah, okay. Yeah. Okay, thanks. Right. Okay, so that's the main lemma. So how are we on time? Oh.
Oh, I forgot about it.
Yeah. Oh, that's 5 minutes. Or is that a question?
No, you have more than 5 minutes.
Okay, so what's the question?
If you can say, I know that you, again, same as Marco, you said not to worry about, but can you just give some sort of a hint or overall, what does it mean to be hard relative to F here?
Yeah, so what it's going to mean hard relative to F, it turns out that it's going to be, you want it to be harder to non-deterministically approximate G. Yeah, there's you can ask what the non-deterministic complexity is of giving a small one-sided approximation of F, and you want that complexity for G to be higher than the complexity of F, or whatever that means. Don't worry if it doesn't make any sense. Okay. Now I want to tell you a little bit about the proof. Again, I'm not going to be able to tell you the proof, but I want to tell you some part of the proof because I think it's pretty cool, because it's an algorithm. And I hesitate to say algorithm here because we already have algorithmic ways to prove circuit lower bounds, and this is not like algorithmic method style stuff. This is just but it is an algorithm that operates on circuits. And informally, the way that we prove this lemma is that we say that there's some algorithm A that if you feed this algorithm as input some formula for h of depth d plus 1, like if you have a formula for h that like satisfies these two properties, it's or topped and has depth d plus 1, and let's say that formula has size s, this algorithm is going to output one of 3 different formulas. either, don't worry about what this says yet, either it's going to output a small formula for f, or it's going to output a small formula for g, or it's going to output a even smaller formula for g that like yeah, okay, I guess I need to say it more detail. Okay, so what's going to happen is you're going to feed in a formula for h, and this algorithm is going to look at your formula and construct smaller formulas for one of two different functions. Either it's going to construct a small formula for f, or it's going to construct, this turns out to be like a small formula for approximating g, or it's going to construct an even smaller formula for computing an even weaker approximation of g. So either you get like some small formula computing a strong approximation of g, or an even smaller formula computing a weak approximation of g. And I should say this is like one-sided error, so like 1% makes sense or something like that.
And there's no restriction on depth. I mean, you don't get any constraint.
Actually, the algorithm does, but I didn't want to write it because it was more words. But yeah, this will be like depth d plus 1. Okay, so just to recap, I think what's cool about the lower bound is actually using an algorithm, which is doing analysis on some circuit. If you give it a circuit, and it's going to look at that circuit and be like, okay, either from the circuit I can construct a small circuit for f, or I'm going to construct a small circuit for g. And I should say I'm like really lying to you here, because this isn't a formula. This is going to be a non-deterministic formula, and okay, these are one-sided approximations. There's like some definitions here, but morally what it's giving you is some way to compute g.
And the algorithm knows, it's not like it outputs something, the algorithm knows what happened, right?
Yeah, the algorithm, I mean, yeah.
It's not like it outputs 3 things and one of them will work.
Yeah.
It'll actually know which one.
Yeah, I mean, yeah, exactly.
So it's a non-constructive proof. Or do you have an algorithm?
Yeah, I mean, I can tell you what the algorithm is, and the algorithm, I mean, it depends how much running time you want.
Although you have an algorithm, the proof is non-constructive.
Okay, wait.
You make a guess, then you verify, then you show that it exists, something like that, right?
So what you'll do is you'll construct the candidate formulas. There's like there'll be like polynomial and n many candidate formulas. You'll just go and see which one, you'll check if any one of them computes these 3 things. I don't know if you call that non-constructive or not, because there's like not that much guessing happening. Anyway, did that answer your question, or?
No, but it's okay.
Okay. Right, are there any other questions? If you want, okay. So I can tell you how to use this to prove the lemma, but I'm going to skip that. If you're interested, you can. I mean, basically what's going to happen in the lemma is you're going to set things up so 2 and 3 never happen, so only 1 happens. And if 1 happens, what you know is now you've constructed a small depth d formula for f, and this thing has size s minus something, and then like if you like rearrange the terms, now that what you've just shown is that like the size of some form, this formula for h is actually larger than what's in the lower bound. But yeah, I would say the takeaway from the slide should be there's kind of an interesting analysis algorithm you can do on formulas. Yes. And okay, if you want to know what the algorithm is, okay, if you want to know about this slide, you can ask me, and I'll go back to it. But somehow what it's doing is, you take phi, you break it up into its depth d subformulas. So phi is a depth d plus 1. You break it up into its depth d formulas, and then you output a few different things in various cases. I don't want to tell you all about all of them. The coolest case is you pick some random subset. You pick basically half of these at random. You pick half of the phi's at random. You OR them together, and that, at least in one of the cases, is going to compute g most of the time. But I just want to give you a flavor of what this algorithm is doing. Somehow it's like looking at the subformulas and doing something with it. All right. So how much time is left? Okay, I'll keep talking while this is happening. So one question you can ask is, does this proof naturalize?
30 seconds.
Okay. So we separate like one class of formulas, something with certain depth and size, from another class of formulas. And what's interesting about this is it doesn't really fit into this natural proof framework so much. It doesn't seem to be very constructive because like the lower bound being used is actually kind of like the quantities involved are NP hard to compute. Seems to avoid largeness because like the lower bounds really only apply to these very special direct sum functions, not to random functions. And yeah, I don't know. It doesn't really seem to fit into this framework. Although this is like a very strange separation in that it's like about the size depth formulas versus size depth formulas of another thing.
Do you think there might be, I mean, any other proof sort of related to this which gives you an explicit lower bound and also has these two properties that it avoids constructive enlargements? Because one of the issues with this is that it's not an explicit function.
Yeah, but I guess you have to be worried about like this 2 to the O of d sub n. Like if you have an explicit function there, then that'll like.
Yeah, no, I don't mean this result. I mean
Oh,
this
you mean
proof
like
technique.
Ryan's? Oh.
I mean the proof technique because I mean the fact that it avoids constructive enlargements is interesting, but yeah, but then you're not getting a low bound for an explicit function.
Oh.
So I'm just wondering if the technique might be useful to get something for an explicit.
I see. So if you can replace the random functions in the construction with a function with certain properties, and you can write down what those properties are, and then this would be a specific function. Is that what you're asking?
Yeah.
Okay. Yeah, that is possible. Okay. What does this have? I'm going to skip this and finish up. All right. So thank you very much for listening to my talk and humoring me about my salt. I hope this talk was worth its salt. And yeah, if you have any questions, feel free to ask.
Okay, hold on.
So when you say it doesn't seem to satisfy constructivity
Yes.
because some of the quantities there are NP-hard to compute, what exactly do you mean? Like formula complexity or what is NP-hard to compute?
Oh yeah, okay. So the thing that's hard to compute is computing L sub d is NP-hard. So like this lemma is phrased in terms of L sub d quantities.
Okay.
And it turns L, and actually what happened was I wasn't trying to prove this separation, depth gap separation. I wasn't trying to prove it. I was trying to prove that this quantity is NP-hard. Trying to like understand the MCSP problem for that. And after I proved it, I looked at it and I was like, hey, wait a minute, doesn't this apply something? And so it just fell out of it. I wasn't even trying to do it, but yeah. Did that answer your question?
Yep.
Well, there is a question in the chat from Conley. Can you efficiently sample the full table of the part function?
Yes.
So to prove that there is a large gap between these between LD and LD plus 1, you first picked a depth and then you found the function.
Yes.
And you said that we don't know if like for a particular function which works for all depths, if this bound works for all depths or not.
Yes.
I don't know that. What's the difficulty with that part?
I guess the difficulty is I'm constructing this function kind of step by step. So like if I don't know how to I don't know how to come up with like the I mean what you'd want to do is you want to consider like the limit of this function, and I don't know how to do that.
Do like Hanlin said, if you have a PRG, can you de-randomize the sampling? So
Yeah.
so universal de-randomization would make your lower bound explicit.
Yeah, but it needs to be a PRG against non-deterministic circuits.
Oh, cool. Okay.
Yeah.
One last question?
You know what's the best additive gaps that we have in sequence against a single function? Maybe not 2 to the n. So the sum.
So I guess parity would give you an additive gap of 2 to the omega 1 over d. Wait, is that what you're asking? 2 to the n to the...
That would be parity over all the variables, right?
Yeah, parity over all the variables. Oh wait, maybe I didn't understand your question.
No, okay, no, that's the answer.
Oh, that's the answer to the question. Awesome. All right, thank you very much.